Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So my name is Phil Chow. I'm with the Communication and Collaboration Systems Group, and it's my pleasure today to welcome Yuval Cassuto. Yuval is a recently minted PhD from Caltech, Shuki Brooks Group, and his specialty has been coding for storage and also network coding, and we'll hear from him about his storage codes.
Thanks, Phil. Thanks for coming. It's a pleasure to be here. A long time ago, sheep were the key asset to both affluence and influence. If you had many sheep, you had a lot of power. The problem is you could not keep the sheep at home in the safety of your house. You had to move them around, and that's why sheep were prone to various types of risks. They could be eaten by wolves, they could fall from cliffs, or just get sick. The modern day equivalent of sheep is information. If you have a lot of it, you have a lot of power, but it also gives you some headaches. What can we do to help? So here, this green patch is this talk, is the subject of this talk. How it is obtained, we take the area of information theory, and we project it through the field of storage system engineering. So basically, each green topic of this talk is a mix of a yellow problem from storage engineering and a blue solution from information theory. Let's look on a general storage system. Up here, we have the physical media of choice. It can either be magnetic, semiconductor, micromechanical, or whatever you find that works. Down here, we have user data. And now the question is how the storage system helps storing the user data on the physical media. So we have another block, which we call read-write interface, which converts between the continuous nature of the physical media and some discrete representation of information. The fourth component is very important, the error-correcting codes. And what they do, they clean up the aggregate unreliability and imperfection of the system to provide reliable information to the user. Now, the main objective of this work is to take the error-correcting codes and bring them closer to the interface and media. And why do we want to do that? Of course, because Shannon said so. Claude Shannon, in his founding paper of information theory, wrote the basic theory in plain words. The redundancy of the error-correcting code must be introduced in the proper way to combat the particular noise structure involved. So basically what Shannon tells us is that the error-correcting codes need to know other layers of the system to get a good error correction. The problem is error-correcting codes do not really fit well the other components of the system. Here you see the smooth curves, and here the spiky edges. And why is that? The media and interface are statistical in nature because they represent some physical phenomena, while error-correcting codes are combinatorial objects. In addition, we have up here complex physical mechanisms, but from the error-correcting codes, we expect some error control guarantees. We want to tell the engineers what they can do. And as a physical entity, we have multiple reliability issues. While it's known that to design an error-correcting code, you should settle for simple design objectives. So to bridge those two, we introduced an error model, usually. And an error model, on one side, on the upper side, it tries to capture the unique properties of the media and interface. And on the other side, it tries to provide simple enough requirements that will be amenable for design and analysis of error-correcting codes. Now, given the error model, if we can construct the right codes for this model, we can have a more cohesive system that works well. Let's summarize the contributions, the topics of this talk. On the practical side, we present fast and dense flash storage, methods of improving the density and speed of flash storage. In disk arrays, we show how we can have how schemes can be devised for correlated failures, for failures that are not independent. And we also have some constructions for codes for disk arrays that are highly regular, and then they have low complexity of implementation. The same topics can be discussed on the theoretical side. On the theoretical side of the first bullet, we have codes for a model which we call asymmetric limited magnitude errors. For this contribution, we devise the model of clustered erasures, which we will discuss later. And here we have codes that are lowest density and are systematically cyclic. Hopefully, those ideas will be clarified later. Now, in general, since we saw this interplay between practice and theory, this slide will present the flow between practice and theory. So we start from a practical problem, and we devise some abstraction of the problem to be amenable for the theory. Then we maximize the power of the theory in handling the abstraction. And finally, we validate what we did in theory back to the practical world and see how well we did. So the scope of this talk will be theory, but enough from practice to allow those round trips. Is the introductory part clear? Because I want to move to the more specific. Are there any questions? Okay. So first we talk about multi-level flash cells. What is a multi-level flash cell? It's a semiconductor device that, using charge placement, you see the electrons here, the level of the cell can be put in one of Q levels. And Q is a variable. Here in this example, it's 16. Now, the motivation to study flash is obvious. Flash grows very rapidly, both in the volumes of storage that it offers and also in the number of applications that it serves. But still, flash needs a push to be competitive with other storage media. So that's the purpose of this work. So engineers like to talk about problems, so it's a good thing to start with. What are the main issues of flash storage? So to do that, we'll see how we program a flash cell. So think of a matrix, an array of flash cells, and let's say we want to program this cell here. What we do, we bias its row. It's called word line, that's the W. We bias its column. Bias, I mean we apply some voltage to some of its legs. And we hope that only, that's basically programming. We want to add charges to this cell. However, because of relatively poor isolation, that is the secret, that's the secret of flash, other cells on the same row or the same column get charges. Even though we do not want them to, that's what happened. So that's the dominant error of flash storage. And once we know this fact, we observe that flash errors have two distinctive properties. One is that they are asymmetric. As you saw in the process, we only added charges. So we think of storage upward. The errors will only add charges. And also, since the isolation is there, it's not perfect, but there are physical mechanisms that prevent large amounts of charge to be added, then the errors will have low magnitude, typically. So an error from 3 to 5 is much more likely than an error from 3 to 9 here. So those are the two immediate observations. Once we have those observations, we come up with an error model. So C is a vector of length n, which represents what we want to store on our memory. R is what the corrupted version, what happened, the vector that is stored after some potential errors. And now we define the error model that for each I, the difference between Ri and Ci is more than 0, which means asymmetry. We only go one direction. And it's not bigger than L, which means we have limited magnitude of the error. And also, for the whole vectors, we say how many errors we allow the model to introduce. And that's a measure of the severity of the errors. So we have two parameters, L and T. And we call this model codes for asymmetric limited magnitude errors, which we call in short ALM. Now these are the two parameters, L and T. And now the research problem that we can ask is find the code, C, which is a subset of the whole space over the alphabet Q of length n that can correct T errors of this type, ALM. And we want a general solution for general N, L, and T. Is the research problem clear what we want to do? Right. No, currently you're right. Here we assume implicitly some block. So, no, we group n cells into one code word. And now we limit the number of errors in this group, T. You can do it cleverly, do it vertically or horizontally, but that's we went down in the level of abstraction. Now we talk about some abstract block of size n.
Well, I guess after you programmed a lot of cells all over the place and the errors. Maybe you couldn't get anything out of that. This seems like it's not obvious. Okay.
Yes, you definitely can take advantage of the architecture. But you do it later. You first solve the more basic problem. So first, before we want to start constructing codes, what does it mean? C is just a list of words over the alphabet. It's not all the words. It's some subset of the legal words. And what does it mean that we want to correct? So before we construct codes, we need to have some method to analyze whether a list of code words can do the work. So for that, we define some distance measure between any two vectors. I will not get into the details. But given two vectors over the alphabet, we define this distance between them. And now we have this theorem that a code C can correct T ALM errors if and only if this special distance is T plus 1 or more for all distinct vectors in the code. So you can take the list, compare them, compute DL for each pair, and then you know if you do well or not. And the nice thing about it is that it's both a necessary and sufficient condition. And that will help us both to construct codes and to prove that they are optimal. Because
what is N?
Big N? That's what I meant when I said I will not get into.
Oh.
Yeah, I just added here for visual impression, but I won't get into the details. The important thing is that given a combinatorial property of the list of code words, we can say whether we can correct the errors or not. And it's the same condition is both necessary and sufficient, which is allows us to have tight bounds. Because if it's both sufficient and necessary, it means that it can provide construction, but you know that any construction will have to satisfy that. Yes, that's the idea. But here you have another condition for doing well. Let's not get into it. So let's see an example how we constructively correct asymmetric limited magnitude errors. We have a vector of all even numbers, and we have two asymmetric errors of magnitude 1 that brings us to this word. Now what we do, we take this vector and find the minority between even and odd, and we see that 3 and 1 are the minority symbols. They are odd while all the rest are even. And now what we do, we just decrement. Since we know the error model, we decrement those two symbols back into the original vector. We can do the same now with all odd numbers. Again, we introduce two errors of magnitude 1, getting to almost the same vector. But again, we do minority, and now the even ones are the minority. We decrement them and go back to the original word. So basically, this code of either all even or either all odd numbers is a length 5 code that can correct any two errors of magnitude 1. So we have the first example of a code that corrects ALM errors. Is that example clear? So let's go behind the scenes of this example. So we have those two vectors. We take the mod 2. We see that we either get the all 0 word or the all ones word. And now we know those two words. Those are the binary repetition code. And the whole idea of this code construction is that we use some properties of known codes over low alphabets, in this case the binary repetition code, to derive properties of codes over higher alphabets for asymmetric and limited magnitude errors. And that's the general construction. Given some code over a low alphabet, and the alphabet now is of size L plus 1, think of L as much smaller than Q. Q is the big, the flash alphabet, but now we only care about codes for low alphabets. Now take C to be all the words of Q, of the big alphabet, such that the symbol-wise modulo, L plus 1, falls into the code sigma. That's the general code construction. And the theorem tells us that if sigma corrects T symmetric errors over the low alphabet, then C corrects T ALM errors over the large alphabet. And the key here is that those codes are well studied, codes for symmetric errors. So we can use known codes over this, in this area, to get good codes in the new error model. Is that clear how the construction works? Now, known results exist for the special case of T equals N. T equals N means that we want to correct all. We don't limit the number of errors within the vector. We only limit the magnitude of the errors. That's a result by Al-Schwede et al. And it turns out that this is just a special case of our construction where you take sigma to be the trivial code that includes only the 0 code word. Now let's see an example how we encode. Yes?
So can you go back here? So how do you encode information?
No, so the modulo falls into this, but you still have, you only restrict the modulo to have no information. But you still have a lot of information in the upper parts. In the more significant, you can see it here in this example. So think of I will get to it later. So that's an example how we want to encode information into flash cells with this property of correcting asymmetric limited magnitude errors. So the user gives us 18 information bits in this example, and we want to encode them into levels, into cells with 8 levels, Q equals 8, and we want to correct a single error with magnitude 1. So how do we do it? We look only on the top row of the information, and given the parameters, we encode it using the binary Hamming code. And we add some parity bits here. That's the redundancy that we add. And now we use the standard conversion between binary vector and integers between 0 and 7 and get the following code word over a code C that we defined before. Now back to your question. So think of here as having no information. You restrict all those to be zeros. You can still have unrestricted information on the other rows. So the fact that you restrict the modulo to carry no information doesn't mean that your code word doesn't have information, because you have other parts of the information that are not in the modulo. So in this case, the restriction is lower. We don't use the whole zeros. We can still have 4 information bits on the top row. Now let's see how decoding works for the same example. An error is introduced here. It takes us from 3 to 4. Now notice that even though the encoding looked on only the top row, this error causes bit errors in all rows. So from 0, 1, 1, we went to 1, 0, 0 because of the error. And now the question is, how can we correct it? So indeed, we do look only on the top row, and we apply it into a Hamming decoder. Now what the decoder tells us is that here we have a problem. But if we just correct this bit, we'll still have residual errors in those two rows. So what we do, we use the decoder more cleverly. The decoder told us that here we have a problem, so given the error model that we are aware of, we infer that a +1 error happened here, and now we go back to the original word over the high alphabet and just subtract this 1 back into the original. And now we get the correct information, even though we looked only on the top row for encoding and decoding. Is that example clear? Now we want to evaluate what we do, whether is it a good code construction or maybe it's not that good. So those are proof, those are results that show that it's a good code construction. One is that we have asymptotic rate optimality for many parameters, which means you cannot asymptotically you cannot construct better codes than those in terms of rate. Some codes are even better than that. They are perfect. And you can for some parameters, you can absolutely not construct better codes than what this method allows. And we compare to the best known alternative using some known codes, and we show improvements, both in terms of amount of redundancy and complexity of encoding and decoding. Now, those two will not be discussed. Let's see asymptotic optimality. What does it mean? So that's the theorem. The construction is rate optimal. It's optimal in terms of rate, asymptotically, if L equals 1 and for any t, or for any L, any magnitude, if t doesn't grow too fast compared to the block length n. And the proof idea, here we have the construction. So we started with the code for symmetric error. We had some inflation, and we got the code for asymmetric limited magnitude error C. The idea is to prove the other direction, to prove the converse, that if we have codes for asymmetric limited magnitude errors, with some deflation factor, we can get to a code for symmetric errors. And that will, if it's a tight, if j equals k, it means that the code is optimal. Basically, the reason is that C can be upper bounded by j and the size of the best code for symmetric errors. So that's the idea of how we get upper bounds on sizes of codes in general. And in particular, what we found is that we can do this trip back, but we have to have a stopover. So if we have a code for asymmetric limited magnitude errors, we can have codes for asymmetric errors without magnitude limit with the same deflation factor that we had up here. Now, to get from codes for asymmetric errors to codes for symmetric errors, we have either a constant or polynomial deflation, and those are negligible compared to the exponential number here, which means the codes are asymptotically rate optimal. Because asymptotically, the deflation factor is the same as the inflation factor. So here we discussed the basic code construction, but we have a couple more. One is to move from putting the parity on one row to putting the parity on dedicated cells, which is better for practical implementation. It gives more efficient updates. So for that, we construct systematic codes. That's how you define in coding theory codes that you can separate between parity and information, as we have on the right side. And also, we may have some secondary error mechanisms that introduce symmetric errors, errors that are two-sided, but still with limited magnitudes. And for that, we have a code construction to correct simultaneously asymmetric limited magnitude errors and symmetric limited magnitude errors at the same, using the same code. So those are two extensions of the code construction that we saw before. Now here's an idea of a non-traditional use of an error-correcting codes. Typically, we use error-correcting codes to combat uncontrolled errors that happen. But here's a different idea. Why not use asymmetric limited magnitude codes to speed up flash programming? We want to use the codes to program the device faster. There are obvious questions. One is how. And the answer is we can allow less accurate programming in a controlled way. And in this way, we can save time, and the code will take care of the inaccuracy that we introduced. And another question is why? Is because small tolerances, very small L's, can lead to large time savings in terms of programming. And let's see how we prove those ideas. So here is a flash cell, and we want to program it. Let's look on the ideal programming. Ideal programming means that we want to start from some level 0. We want to get to some level 7. That's an example. What we do, we apply some pulse that we carefully devised, a pulse that should take us from 0 to 7. And since it's an ideal programming scheme, what we get in the output, 7. But in practice, the ideal doesn't work, and that's a more realistic programming algorithm. So we start from 0, we want to get to 7. We apply a pulse that we thought about a lot. We design it carefully. However, in the output, we see a 4. What we do now, we read back the 4. Now we want to go from 4 to 7. We apply a different pulse from 4 to 7, but we only get to 6. So we repeat this process. We read, we apply a pulse from 6 to 7, and this time we are lucky. It's not luck. As you see, the pulses become more conservative, so we get to the right point.
So what if you overshoot, say you want to go to 5 pulses too strong?
Yeah, overshoot is a very important concept in Flash, and I will get to it in the next slide. Yeah, basically you want to go to the right level quickly, but you really don't want to overshoot. Because in Flash you cannot erase selectively, so you cannot go down on one cell from level 8 to 7. If you overshoot, you basically need to erase the whole block, which takes a lot of time and adds wear to the device. So you really want to approach carefully from below. And that's the main idea here. We'll see it now. So we want to come up with a model. So what we saw before is some optimized algorithm. The pulses are optimized in some way. We want a more amenable model. So given an initial level I0, final level IF, we model the output increment as an exponential process with a parameter that depends on I0 and IF. Basically, since the programming is a probabilistic mechanism, we think of exponential as a good model for it. So now we have only one parameter to describe our programming algorithm. The problem is it's one too many. How do we set this mu to describe the actual optimization of Flash programming? And given the comment that we had here, that's a fact, that a major consideration of programming algorithms in practice is to avoid overprogramming, because it's very painful. So that will also serve as a consideration of setting up mu. And how we do it, we basically make sure that we fix the probability of error programming. We see it here. That's the exponential distribution for any levels, for any difference between the final and initial levels. We fix the area here, which represents the overprogramming probability, to be a fixed number. And for each pulse that we want to apply, we model the distribution as exponential with mu set in this way. Is that clear? How we?
So the method you apply, trying to estimate the probability of overprogramming, and you just assume that the code can tolerate this error probability. So that allows you to program faster. Is that basically the method?
The idea here is that I want a model to analytically show how much I can save by applying a code that can tolerate L levels.
Okay.
Basically, if you can tolerate L levels of error, it means you can stop earlier. You don't really need to get to 7. You can stop before. And now the question is, do you save a lot, or maybe it's negligible? And the model is used to quantify these savings, to give some analytic numbers sorry, to the amount of savings that the coding scheme allows. And that's exactly what we have here. We have analytic results. The number of passes that you can save behaves like that. It's a log of L. L is the number of levels that the code tolerates. And K is some constant that depends on the overprogramming probability. But most interesting is how many percent we save. What is the speed up that this code gives us? And we see it here, and that's the median. And once we plot it, we see some interesting facts. We see that for L equals 1, we already save about 20% of the programming pulses. And another thing, we see that we exhibit diminishing returns. So if we try larger L's, it doesn't help that much. So it makes sense to have a code for really low magnitudes. And that's a very good motivation to study this model. Because if you use some off-the-shelf error-correcting code, basically in this case L is very large, it doesn't help you much beyond what you can get with a very low magnitude. Yeah, that's an example for 32 levels. A cell with 32 levels.
Currently in flash memory, error correction code is employed for large block. It seems the current code is designed mainly to allow overshoot. Or you have you assume it's a asymmetric error, right? Basically the error can be higher than the level stored, but never be lower, right? In the flash memory, in addition to the error caused during the write stage, you can have other cause of error. For example, during the recycle or the other cycles, the gate may be stressed and lead to negative errors. How can you combine this code with other code to protect the other kind of error? So let's say you have two kind of error source.
Yeah. So basically, what you want to do is differentiate. So if you observe one error mechanism that is dominant and it has some unique properties, then you want to find a code for that type of errors. Now you will see residual errors that are not covered by your model, but that means there will be much lower because you remove the problems of the dominant ones. And you can always employ another error correcting code to tackle the residual errors that come from secondary error mechanisms. And those will be, you need a much weaker code for that. You don't have basically as targeted as you can be. If you have a good picture of the real errors, that means you can save in redundancy.
That you can still use this code to correct the asymmetric error, and using a weaker code, for example, currently it's a very large block BCH code to correct the other category.
Exactly, and the BCH would be simpler, lower redundancy and lower decoding complexity.
Here's my observation. If the other errors do occur, you are creating more error in the BCH code. So for example, just give an example. Let's say I'm trying to write 4 in value, which is binary 100, right? Let's say this thing creates 1 bit of error. And it's basically going lower because of the stress. So it goes to 0, 1, 1, right? Now when I apply your code to decode it, it will decode to something, let's see. Basically it will decode to something very different and even push it even lower. I think 0, 1, 0 or something. Because you always assume the error is going above. Now if you look at the bits, all 3 bits are wrong. So when you parse that information to the BCH code needs to be much stronger in trying to deal with that.
No, but basically you can minimize, what you refer to is called miscorrection.
Yeah.
That's a standard trade-off. When you apply an error correcting code, if the errors exceed the capability of the code, then you may not just fail to correct errors, you may introduce more errors. That's a standard trade-off. But you can use some tricks here to minimize that, because you can, what I showed there is you map the binary vectors of each column to a number in the standard way. But you can apply better mappings, like gray mappings that minimize, even if you miss the right level, you did not correct to the right one, or even miscorrected one below, the number of bit errors that you observe is small, and you get it from the mapping. The mapping will control the number. It's not catastrophic. You may see more errors, but it's not in a catastrophic way. Yeah, that's always a challenge, how to pick the right error correcting code to handle many. You don't want to overpay in terms of redundancy, but you don't want too many occasions where the errors exceed your capabilities, because then miscorrections may come. Yeah, but you have mechanisms to control the miscorrections observed by external error correcting codes.
Have you looked at, for example, the flash technologies that exist now or are going to exist soon, and do they in fact have primary modes of error that are significantly higher than the secondary modes, or are you going to be in a situation where in fact there's a couple primary modes or some fairly equivalent primary modes such that you can't come up with one ECC or one error correction?
Yeah,
we handle both.
We did not get a chance to do experimental study of particular processes.
Looking at the technology and talking to the physicists, so I mean, there's a lot of different ways flash can fail, and whether or not current or the next set of technologies have in fact a primary mode, I think is an open question.
The way I came up with those models, I just read the flash literature and things that I counted the number of times issues are mentioned. And disturbs are mentioned very frequently. Disturbs, what the error model, the error source that I discussed here, where you program the wrong one, the wrong cell, those seem to be the most painful ones. And engineers always can play with things. You can make disturbs better, but then you introduce some other problems. So at least you have some another knob to turn when you design a flash device. If you can make one more significant, then you may be able to improve the density. But the control errors that we discussed in the last part, that's independent. It's errors that you introduce, so you don't care about.
The idea of forcing a primary is interesting. That's what I just took out what you just said is, if you do have a situation where you've got two fairly strong error modes, if you can actually gain an advantage by forcing one of them to be a little stronger and the other to be a little weaker, and then focus your error correction on the strong, you may end up with a net win. Right? Took out what you just said.
Yeah, the flash industry is moving. That's what happens when you mature from the error-free regime that you try to space everything out so you don't have any problems in any way, to a more realistic mode where you try to, using error correcting codes, you try to find the best trade-off between the design of the device and adding redundancy. And then you have more freedom to design the device to get better densities. So we are almost done with Flash, but before that we want to show that our model is realistic. We picked some idea of model and we want to compare to experimental results. These results show how you program a real Flash device, and the horizontal axis is the sequential number of the pulses. Here is the current that you program to. And as you see, those programming sequences, they start pretty well. You do a lot of progress in the early steps, but then they flat out. And that's exactly what our model predicts. And as you see, if you can tolerate L errors, this gap, you see that for small L's you gain a lot because you save all those pulses. But if you increase L much more, then you see diminishing returns. You'll not save too many additional pulses. So basically what this slide means is that the experimental data shows us that the model makes sense. And here, part of the reason the curves flat out is because you don't want to overshoot. Basically, you become more conservative as you approach the right level. And that was used in our model too. So here we say 5 pulses for that L. Is that hard to have asymmetric limited magnitude error correcting codes in a flash device? The answer is no. That's the old way of having error correcting codes in a flash device. Basically, you have the flash cells. You have some analog to digital conversion that reads what the cells store, and then you convert it to some alphabet for the error correcting code, and you output the estimates on the right code word to the user, hopefully cleaning up the problems of Flash. Now, what we propose is only slightly more complex. You have the same Flash and A to D here. Now you have an additional step. You take the modulo of what you read. You apply a decoding of the error correcting code. But instead of passing the code words to the user, what you do, and we saw it in the example, you subtract the error estimates of the error correcting code from the original symbol here on those adders, and then only then you pass the estimates of the right code word to the user after some additional alphabet conversion. So with the addition of simple blocks, those adders and this modulo, you can achieve a more targeted error correction.
So, if you have other errors than the stress errors, I assume you still have to have an ECC decoder module after alphabet conversion.
Right. You can add it here. You can add another software or hardware ECC on the top layer. But here you will see a much cleaner, if the error model is correct, you will see much cleaner data there.
I'm just wondering why we can't basically design a combined ECC code which deal with both errors. It seems to me that will lead to simple design, since you will need the upper ECC module and other error.
As I said, it's pretty hard to optimize an error correcting code to many design constraints. You want to, it's very hard. In practice, you don't have very complex models for error correcting codes. But I had something to say, but I can't remember. So basically, you add small complexity to the system and get a more targeted error correction. Okay, we are done with Flash, so if you have any question for that, we'll move on to the next topic. So now we move from the individual device level to the disk array level, to the more enterprise storage type of problems. So a storage device leaves the factory. It was tested, and it has guaranteed to work 3 years. But nobody sleeps well at night without backing up this device. And in the enterprise storage, things are even more problematic. If you have many of those devices, then it will not take you long to lose your job, maybe 3 months, because of lost data. So you want to add some reliability to the array. You don't just trust the reliability of the device, you want some group protection, and that's the area of array codes. What are array codes? So each column represents a data device. You basically add some parity devices that don't carry information. They are just used to protect. And if devices fail, you use the parity devices to recover their data, hence not losing any valuable information. Let's see an example of how array codes do this task. So the white cells are information cells, and the magenta ones are parity. Those are cells whose values are computed using simple XOR, exclusive OR operations from the information. Now let's say those two devices fail and we cannot access them anymore. How do we reconstruct? We can compute E by taking C and sum it up with all the parity cells. And since those are exclusive OR operations, everything will cancel out except E. All of the letters appear an even number of times except E. so you can reconstruct E. Then D can be reconstructed from E and from non-failed cells. We can have a sequence of those. And then now we can recover all 4 bits, and we didn't lose any data. A very important notion of array codes is the update complexity. Because now you want to protect the data, you have to maintain the consistency of the code over the data, which means that if you update an information bit, you need to update some parity bits. And that that slows down the writing process because you need to access more cells and more devices. And now we want to quantify this issue, and that's called update complexity. Let's see an example. We forget about the information bits, and we count. And we count that A, B, D, and F each appears twice on those parity bits. And we count that C and E each appears 3 times. And that means we take the average over all bits, and the average update complexity is 2 1/3 for this particular code. And that means that on average, if you update one parity bit, one information bit, it means you have to update 2 1/3 parity bits. And of course, you want to keep this number low, because a high number means slower writes. So prior work on array codes, as I said before the talk, it's a contagious disease working on array codes, and it went from a mentor to his protege, and you have Chen Huang here, that is a part of the chain. I'm somewhere here. And let's discuss particular works that are relevant. So Blum-Roth introduced algebraic array codes, basically code constructions that use algebraic methods to get good correction capabilities. Blum-Brook introduced even-odd, which is used in practice. If you buy disk arrays from IBM or I don't know exactly where, use those even-odd codes. Brook and Shu introduced B codes. We'll discuss them later. Those are also codes with very good properties. And generalization was introduced by Roth and Louis Dore. And finally, Shu and Wang introduced some variation on even-odd. Those are some of the significant works in that area, and our work relies on them.
Okay. So the metric that you're trying to use for this is update complexity, the number of bits that you have to touch. You're talking about storing really on disks, not in memory systems, right? So the cost to write a bit on the disk depends on what you just did on the disk. So the first approximation, all of the cost of writing to a disk is moving ahead to the place on the disk, and none of it is moving bits. And that's pretty close to right. So I think a better metric for this is how much it costs is how many of those columns that you have to touch, not how many actual bits that you have to update. And in this particular case, if I look right, which I did real fast and look right, any of the letters appears in one of the other columns. So all of the updates you have to write in both of the variables. So that's the metric that matters.
Yes, that's another metric. So it depends on the application.
In terms of actual time that you spend, that's what counts. Because it takes you 10 or 15 milliseconds to get to the thing. It takes you microseconds to write an extra sequential sector. It really is the only thing that matters.
Yeah, so as theoreticians, we don't tailor our work to particular design or system. We are inspired. So yeah, the current main usage of those codes is for disk arrays, and in that sense, you are right. But
Taking the wrong thing to optimize, which isn't. I mean, it's great for you, right? Because it gives you a new problem that somebody else doesn't work on.
No, actually, I will show improvement both for that update complexity and the whole disk update complexity, in both. So I'm doing well. So if we want to correct multiple failures, let's say R failures out of the disk arrays, then the best scheme is using the R even node, which is a generalization of even node. And the properties is that to correct R failures, you need R redundant disks. That's optimal. The decoding complexity grows with R. So for any additional failure that you want to correct, you pay in the decoding complexity. And worse than all, the update complexity grows pretty quickly. So we have, for any additional failure, you have to spend 2 more updates. And that's kind of high. So we want to, the idea is to try to avoid this growth. Now we go back to the gap between theory and practice. Typically in theory, when you optimize error correcting codes, you follow this order. You first care about the redundancy, then decoding complexity, and hardly ever you discuss the update complexity of the code. And it turns out that in practice, it's basically the opposite. The most crucial part is the update complexity, because that's something you pay even with no failures. Just to maintain the consistency, you have to update. Decoding complexity is important, and redundancy is, of course, important, but it's not the limiting factor. And speaking to people in the storage industry, that's the bottleneck. Here, that's what prevents them move on to higher failure correction. So we want to propose a scheme that will improve that potentially over the others. And we'll see how we do it. So all previous works on array codes assume that the failures are independent. They basically just tell you how many devices fail with no respect to their locations in the array. That's like saying the channel is memoryless. But that's not the case in practice. If you have a large number of failures, you are likely to see errors that are correlated. They are not independent. And let's see what it means. So here we have 2 examples of 4 failures, 4 device failures. On the top, we have 1 and 3. And here we have 4 isolated ones. Now, since adjacent devices share cooling, they share cabling and power and mechanical stress, we can think of them as failures in them as correlated. And we can think of this failure type as 2 independent events. So even though the failure affects 4 devices, we can think of only 2 independent events that cause them. One here, and here maybe some coffee spill that failed all those 3. And in this case, we can think of it as 4 independent events. And the conclusion is that this is more likely than that. So maybe we want to find codes that are better for clustered failures and maybe not as good for completely isolated failures. That's the motivation. Now the error model, now we characterize the correction not just with R, the number of failures, but rho as well. How many clusters the failures occupy. And the motivation, again, is that row-independent events are likely to affect only row clusters with potentially more than row devices, and for that we have R. Is the model clear, what we want to achieve? So here is an example. Here we take all types of 4 failures characterized by the number of clusters. Here, 1 cluster. They're all contiguous. 2 clusters, we have 2 types. Either 2 and 2, 3 and 1, 3 clusters, and 4 clusters. So that's a new characterization of failures that we propose. And the reason we propose is that we can come up with code constructions that are very good for clustered failures. And the new code is called RC, for random and clustered. These codes have both very good clustered failure correction and reasonably good random. So they're also good for isolated failures, but not as good as for clustered ones. That's a new code family. So for any prime P, you can construct a code that will have the properties that we will mention now. So that's how we encode. These diagrams gives us how we encode the parities. So each icon here specifies an encoding rule for 1 bit. So all the circle bits have some known parity constrained by the code. So you can use this diagram to encode those parity bits. Basically, you compute something from the icons on this side, and that's the result to be put on the parity bit. And that's one parity. We have 4 of them. That's the second one. And the key of this construction is that 2 of the parities are sparse. As you see here, those 2 parities only look on half of the columns of the array, which gives us all the benefits of efficient encoding, efficient decoding, efficient update complexity, both in terms of bit update complexity and full device, as was mentioned here. But that's the key here, to see that we have 2 dense parities, but 2 sparse, and that will help us in improving. Now, to prove the properties of this code, we need some algebraic description. So for the same encoding rules that you saw before, we can formulate as an algebraic parity check matrix. And you see the 4 parity. That's the horizontal parity. That's the slope 1 dense parity. And those are the 2 sparse parities. So the exponents here reflect the slopes of the shapes that we saw before. And to analyze the properties of this code, we use some ring, some algebraic entity called a ring, which basically treats each column as a polynomial modulo this polynomial MP. And we use similar. This same representation was used by Blum and Roth for other codes, but it's very useful here to prove our main lemmas. What are the main lemmas that give us the properties of this code? The idea here is that we want to correct all combinations that fall into 3 even and 1 odd columns, or the mirror case, 1 even, 3 odd. And simultaneously, we want to correct all failures that occupy 2 even columns and 2 odd columns. Now I have to note that each of those separately is easy, or is known at least. So one is your pyramid codes can achieve that. You can apply pyramid codes and achieve a correction of 3 even and 1 odd, or the mirror, with the same cost. And also doing just that is very easy. You just take 2 separate codes, 2 even odd, let's say, and get, again, you get the same property with the same cost. The key challenge is to do both. And doing both is really the secret of getting the clustered failure correction, and we see it now. So now for each type of clustering of the failures, we see what types of partition to even and odd we can see. So this type of failure is always 2 and 2. Here we have 2 and 2. This one can be either 2 and 2 or 3 and 1, same as this one. And only that one has the bad case, 4 and 0, which is not covered by dilemmas. And here we immediately see that our code construction that can correct all 3 clustered type of failures, and it will fail to correct some, but not many of those. And also you can see that in order to guarantee this failure correction, you need both the 2 and 2 and 3 and 1 cases. And that's the progress that this code introduces. Is that clear, the relationship between the lemmas and the failure correction? Now, another challenge is to do it efficiently, to decode those codes efficiently, and for that we need to use some algorithms over the algebraic ring, and we can reduce from p squared to p log cube of p some of the operations, and from p cubed down to p log of fourth power of p. And that allows us to decode those codes efficiently in a complexity that is negligible compared to p squared. And the reason we want it to be negligible compared to p squared is that we want the syndrome calculation to be the dominant element of decoding, and those will be a negligible addition. That will give us the decoding benefits that we'll now see. So that's a comparison between RC, and that's our codes, and the 4 even odd. And we see that in encoding we save 25%, decoding also 25%, 3 kp instead of 4 kp. In update complexity we even save more, 5 instead of a 7. Cluster failures, we can correct all of them, minus some negligible fraction of them. And random failures, we don't correct all of them, but we correct 7 out of 8 combinations. So that's another point on the trade-off between complexity of implementation to correction capability. And to validate that that's a good thing to, good scheme to apply, we can correct, we can show how the reliability of an array that uses this code is compared to a reliability of an array that uses even odd or known codes. And for that we use a standard, that's a standard way of computing the reliability of a disk array. So here we want to compute the mean time to data loss. How much time we are expected to wait before we see data loss in the array. So we have a diagram that has failures. So a failure brings us from a lower state to a higher state. The state represents how many failures are in the system. And once we get to F, we exceed, it means that we exceeded the correction capability of the code and we exhibit data loss. There is a competing mechanism, replacement or repair of devices, that gets us lower to a lower state. And now we want to use this technique for RC codes. And for that, we introduce a special set of states. We call them clustered states. Those are states that represent failures that are clustered. And the reason we do it is because our code is specialized for those failures. So we introduce a failure mechanism, chi, that brings us up to the cluster states. And now given the new state diagram and putting in the parameters of RC codes, we can analytically compare the reliability of RC codes with codes that correct all 4 failures. Here we see that you see that when chi is 0, when you don't have a special clustered failures process in your system, the performance is much worse than a true 4 failure correcting codes. But what we see next analytically is when chi becomes in par with the random failure rate, those curves, this curve approaches the dashed curve, and we get performance that is comparable to a performance of all 4 failure correcting code. And that means if you are a storage operator and you have an estimate on chi, and if it's high enough, it means that you may want to use RC code and not in all 4 failure correcting code, because it saves you in complexity. And you also have a tool, this analytic computation gives you a tool to estimate the mean time to data loss that you will observe. So that's the validation of the code properties on real systems. Now, our final topic, which will be very short, some additional array codes. And for that, what are the cream of array codes? What are the best array codes that exist? These are those that have optimal redundancy. You add the minimum amount of redundancy that you can hope for, and also codes that have lowest density, which means that they have the optimal update complexity. You cannot improve over them in terms of both redundancy and update complexity, and there are a handful of those type of codes. What we do is we add another favorable property in addition to those, and we call it the systematically cyclic property, and that will help us getting a low implementation complexity of the codes. What is a systematically cyclic code? This is the encoding rules of the array code. Basically, the letters here are information, and those are parity. So a systematically cyclic array code means that each column can be obtained by the column to its left by adding 1, modulo 6 in this case. So basically, this column determines all the other columns. You add 1 each time, and you get all the encoding rules of this array code. What's the benefit? That's a non-cyclic code. This is how you have to describe the parity constraints. For cyclic code, it's much simpler. You basically have to specify it only for one column. Each group here is a column. And then all the rest is just cyclic rotation of the same rules, which gives you much simpler implementation. And we summarize the benefits. Compact specification, you only have to specify one column. Simple decoding, fast encoding, simple update circuits. And for some operations, you don't really need to know where you are in the array. And that obviates synchronization in some storage devices. So that's the practical benefits. What we have, those are new families of codes that have all those properties. And here R is the number of failures that we can correct. Now, just an idea of the construction. We take the field, the finite field of size P. We partition it. We use a generator for this field. Now, the way we partition it, we take some element of order R in the field, and we get some partition. All the field elements are partitioned into groups. Now, this idea was used to construct non-cyclic codes. What we do is we take a different route from here. We drop one set of this partition, the set that contains the element P minus 1. We define a permutation on this on the remaining elements. And what we do is we take the sets that we got before, applied the permutation on them, and get DIs. Those are exactly the sets that we saw here. Those sets will specify how each column is connected to the parity bits. And of course, all the rest of the parity groups will be just cyclic rotations of this. So that's the code construction. It's pretty simple, but the proofs are much more complicated to show that it has all the good properties that we promise. So that's it. To summarize, in order to get progress, think of in coding for storage, you need to shoot some arrows that will cross this barrier and hit this wall. So what we have here, we have flash storage and correlated failures. We both defined a new model. But then you have to find codes for this model, and then you have to say how you decode your codes. For the other results, we didn't change the model. The last codes that I mentioned, we just have a new code and decoding. And other results that I work on improve the decoding of known codes. And that's why they only have to cross the decoding barrier. And it doesn't matter which path you take, as long as your errors get to their target, it means you make progress. So if you want to read more, those results appeared in external publications. I also, as Phil mentioned, I also worked on network coding, and I will be very interested in talking to your experts about it. Those couple of interesting results. And finally, future ideas. So what we saw in the ALM coding is that in addition to the usual constraints over the code word that we have in coding theory, we also added some constraints over the alphabet. Because we observed some structure of the alphabet, we opened a new optimization dimension, and each of our code construction is some point on this new 2D dimension. But this idea is much more general. You can come up with other error models which have structure on the alphabet and have other code constructions which are better than just working on this dimension. In terms of correlated failures, so we had a very special case of this idea. We only handled r equals 4 and those two intermediate cases, rho equals 2 and rho equals 3. But that idea is much more general. Of course, r more than 4 is very interesting. We want construction for that and bounds. And also, we only cared about erasures, about failures. You can think of extending it to errors. You want to correct errors with those clustering constraints. Finally, the cyclic codes that we propose are very natural to be decoded using iterative message passing decoding. And the reason is that the highly regular structure of them makes iterative message passing very simple. So an open question is whether we can use iterative message passing decoding while maintaining the awareness of the special error model. Because once you move to the iterative decoding domain, you basically lose the array description of your code. The question is, can you introduce the error model into the decoder to get improved decoding using iterative message passing? And basically, that's the end, and I will be happy to get more of your questions.
So for the last part, the semantic cyclic code, I recall seeing in FAST 05 with IBM works using Blue Gene, the supercomputer to search for codes. So are there any?
Or to search for error correcting codes?
Yeah, that have a cyclic structure. Because they just search for all the parameters just using Blue Gene.
Oh, I didn't know of this project. Maybe I should tell them, because, yeah, basically when you search for codes, you search for cyclic codes, because searching on the whole array is very hard. Basically what you do, you say, I will guess the left column of the array, and then I will complete it using the cyclic rotation. So that's why when you search for codes, you hit those. And the prize is that they're also better in terms of implementation. So it is nice that now you have systematic, you have a code construction that you don't have to search. You know that it exists, and I can constructively tell you what the left column will be, and you are guaranteed to have all those nice properties.
Maybe you can check whether your code is on their icon on their search list.
The problem with search is that it gives you only finite lengths. Here we have an infinite family of codes. So for each prime, you can find this code. But thanks for, I will check.
Questions? Great, let's thank the speaker again.